Hi everyone, this is my Lab 5 report. In this investigation, I model a collision between two carts, where one cart slides down a ramp with friction before colliding elastically with the second cart on the ground. My goal is to combine video-style physics analysis with GlowScript modeling to understand how friction affects momentum and energy before impact. Here's the structure of my presentation. I start with the physical system and assumptions, then walk through the physics model and GlowScript code, show the results, and finally answer several what-if questions. The purpose of this project was to investigate how friction on a slope changes the speed and momentum of a cart before a collision. I use GlowScript to simulate the motion, calculate energy and momentum in real time, and observe how non-conservative forces reduce the energy available at impact. The key ideas here are Newton's second law, energy, momentum conservation, and kinetic friction on an incline. Before the collision, friction removes mechanical energy, but during the collision itself, we treat it as perfectly elastic so momentum is conserved along the x direction. The system consists of two carts. Cart 2 begins at rest on the slope, and cart 1 waits on the flat ground. Friction only acts while cart 2 is on the ramp. After it reaches the bottom, then the motion becomes 1D. The collision is modeled as perfectly elastic. The motion on the slope is computed using the standard Euler method. The downward acceleration is gravity minus friction. This already shows that friction reduces the final speed significantly. When the carts overlap, I apply the standard elastic collision equations. Momentum and the kinetic energy are conserved during this instant because friction does not act during the collision itself. This is a view or a screenshot of the scene in GlowScript. Here's the GlowScript code used to set up geometry, initial conditions, parameters like friction, masses, and the angle. This is the heart of the program, and it is the time loop. It first checks if cart 2 is still on the slope, updates the acceleration accordingly, and then switches cart 2 to horizontal motion once it touches the ground. This part handles collision detection and applies elastic collision velocity updates. The condition ensures that the collision only happens once. Here's the animation of the simulation. Cart 2 accelerates on the ramp, reaches the ground with reduced speed due to friction, and then collides with the cart number 1. The energy graph shows total mechanical energy decreasing while cart 2 is on the slope. Once it reaches the ground, potential energy becomes 0 and only kinetic energy remains. After the collision, the kinetic energy is redistributed between the two carts. The momentum plot shows the total momentum increasing as cart 2 accelerates. At the collision moment, the momentum is conserved. Afterward, the momentum is split between the cart 1 and cart 2 based on the elastic collision equations. In reality, friction is not constant, collisions aren't perfectly elastic, and the carts would rotate slightly. All of these simplify the model but make the simulation easier to analyze. So thus, these are the sources of error. I also explored a few what-if questions to understand how different assumptions affect the outcome. Small parameter changes like reducing friction or increasing slope angle dramatically change the collision speed. What if the friction is 0? The cart arrives with a high velocity, causes bigger momentum transfer, and the cart 1 moves faster. What if the slope and the angle is larger? There is a stronger g sine theta, smaller ug cos theta contribution, and thus a much higher impact speed. Question number 4 for what if is that what if there is a friction on the flat ground as well? The answer is that both carts slow down after the collision and the momentum is not conserved for the system. In conclusion, friction on the slope plays the largest role in reducing cart 2's kinetic energy before impact. The collision itself behaves exactly as predicted by the momentum conservation. Overall, the simulation aligns well with the physical expectations.